And I've just realised I am muted. I will restart that. Hello everybody. How are we all doing? Can you all hear me and see me and all of those things? Is that all fine now? Can you all hear me? Yes? Yes, no, maybe? Yeah, awesome, perfect, thank you. How are we all doing? We're gonna get started in just a minute. I'm Georgia. I wanted to introduce you to my cat who is now upset about being in frame. So say hi to Nemo before he runs away. And goodbye, Nemo. Be free, be free. Yes, so today's class is going to be on intermolecular forces. We'll get started in like 60 seconds once other people have had a chance to show up. But is everybody doing okay? I know we're all sort of stuck inside. If you're in London, it's probably snowing, which I'm finding very exciting today. Let me know how everybody's doing, and I will slowly start sharing my screen and we'll get started with the class. Can everybody see the PowerPoint? Yes? No? Yes? Awesome. Okay, so today's class is going to be on intermolecular forces. So I am going to try to pronounce your name correctly. Tagelma? Hard G or soft G, or I'm saying it wrong entirely. Do let me know. I would prefer to get people's names right if I can. Intermolecular forces is kind of like ionic covalent, something like that, but it's sort of, instead of those strong forces that make up molecules, it's weak forces between them. But we'll sort of get on to that definition better in a bit. If you haven't met me before, I'm Georgia and welcome. I'm the head of education here at SnapRevise. I sort of did a bit of a combo degree. I did natural sciences, which means I did sort of like half chemistry, half neuroscience, and I've been tutoring and teaching A-level chemistry for about 7 years now. So hopefully I can do lots of things to help you guys out. Okay, and as usual, we have sort of some giveaways. So at the end, or sort of right now, if you follow us on Insta and then you like screenshot this class and tag us in your Insta story, then you will be entered for sort of like a free account giveaway. So make sure you do that. If your Insta is on private, make sure you like drop us a direct message so we know that you actually did it. Otherwise we won't be able to see it and you won't be entered, which would be sad. And then at the end, everybody gets a coupon code for a discount. So do stay tuned for that. You can't be bothered to get out of bed around it. I'm so sorry. Yeah. I mean, it's not really the day to get out of bed. Good thing is you don't have to get out of bed for a YouTube class. You can stay in bed. It's all good. Okay. Hello, everybody. Hey, Laura. Hey, Nepal. Hello, Kiana. Our intermolecular, the weak forces between layers in a lattice structure. Depending on the lattice, yes, but we will get to some examples in a bit. Our objectives are to first look at instantaneous to induced dipole bonds and their physical properties. So you may have heard those as Van der Waals or London forces, depending on your syllabus or who your teacher is. We're going to be looking at permanent dipole bonds and their physical properties, and then hydrogen bonds. So we're not going to do sort of, some of the syllabuses like to do this specifically looking at sort of different length chains of hydrocarbons. We're not going to do that. And we're also not going to look at sort of like water versus ice, which also is occasionally on the syllabus. So as usual, at the beginning, I put the spec points. I'm not going to read them, but they are there for you guys to look at. If you sort of download the booklet, you'll be able to make sure you're covering the things in your spec. So that is a really useful thing for you guys to sort of get the hang of looking through your own specification. All right. So before we start on sort of the very intermolecular forces-y material, what I want to do is just make sure we all understand one of the sort of core concepts that we need for intermolecular forces, which is electronegativity. So could you guys in the chat tell me, what you think electronegativity is. Anybody got any ideas? The ability to attract electrons well, says Omar. That's a good shout. Libby says the tendency of an atom to attract a bonding pair. Yeah. Ra says the ability of an atom to attract an electron. Laura says the ability of an atom to pull electrons in a covalent bond towards itself. All of these are great. I'm going to sort of like make this a little bit more full. So those of you who are saying things like tendency to gain electrons, you're not wrong, but you want to be more specific because electronegativity is about covalent bonds specifically. So that's what I'm going to write. So electronegativity is, you could say, the tendency or the power of an atom in a covalent bond. Oops. To attract the electron. That is not how you spell electron. Electron density towards itself. Cool, beautiful. So we have different ways of sort of showing electronegativity in a bond when we're drawing a molecule. We sort of look at it as partial charges rather than full charges, right? It's not an ion, it's not a formal charge. It's just that like some things are partially negative, some things are partially positive. So does anyone remember what symbol we use to sort of denote that, to show that something's like a little bit negative, a little bit positive? What is electron density? Somebody just said, and it's this bit. Oh, Angeline, electron density is basically just sort of, if you think of, I'm going to draw a carbon and a chlorine together. So if you think about electrons sort of in the old way, in the previous model of electrons, you kind of imagine that the electrons are just sort of like sitting, two of them between the atoms, but that's not really how it works. They don't just like sit in one spot. They're sort of, it gets weird in quantum, but essentially you can think of their location as a probability, not as a specific spot. So electron density is a way of describing that. So really, when we're looking at where an electron is, we're saying we know it's in this general vicinity. And if it's more likely to be in one spot, we think that's sort of got a higher electron density. So for example, our chlorine is very electronegative. So the electron density, i.e. the probability of finding an electron, is sort of closer to the chlorine. Does that make sense, Angeline? Does that help? And those of you saying delta for partial negative and partial positive, great. Yeah, you are correct. So it's little delta rather than big delta. Big delta is the one we use for our enthalpy, but little delta. So we've got delta negative for partial negative and delta positive. So the last thing that we want to talk about in terms of like knowledge we need for all of this to make sense is sort of dipoles. So can anyone tell me sort of what a dipole is? Like, what do I mean by a dipole? Hi, Marion. Permanent, induced, temporary. Yep, those are types of dipole, but that doesn't sort of tell me what the dipole is, but they're definitely types. The arrow, molecule with different regions of charge, and yes, an uneven distribution of electronegativity. So can anyone give me an example of a molecule that like definitely has a dipole, like definitely has one atom that's really electronegative and one atom that's not very electronegative? Yeah, charge difference in electronegativity, molecule that has a delta positive, delta negative. All of these are fabulous answers. So Zara says fluorine. Yep, fluorine is sort of an atom that would have a dipole. Yeah, water's a good one because we all know that oxygen is very electronegative and hydrogen is not. So there's a dipole in this molecule, because our oxygen is electronegative or electropositive. Did I already say that? I already did, so I'm just going to write it in. I gave you the answer. So we have a dipole in this molecule because the electron density or the charge sort of over the whole molecule leans towards our oxygen. So that's what we mean by having a dipole. What about carbon dioxide? Does this have a dipole? What about chlorine? Chlorine would also form a dipole with things that are less electronegative. Yeah, Libby says no. So carbon dioxide does not have a dipole. Anybody got any ideas about why? Why is there no dipole? It's symmetrical. Yeah, so Ria says the dipoles cancel out due to the shape. Agatha says they cancel out. Ghazal says symmetrical. All of these are correct answers. So like technically we know that the oxygen is going to be electronegative compared to carbon because of where it is on our periodic table. But its linear shape, as Laura is saying, means that your oxygens pull the electrons sort of equally. It's like a tug of war, and a tug of war with two people that have the same strength. So it means that you don't have any sort of uneven charge distribution. The charge is sort of evenly throughout the molecule just because of the shape. Is everybody good for me to move forwards? Because that sort of covers our intro. If not, if so, one of those. What if the shape of the molecule was bent? If the molecule was bent, then you would have an overall dipole. Yeah, all good? Cool. All right, onwards. So we're going to start looking at our types of intermolecular force. And I've kind of started with the most complicated one, just because I like to throw us in at the deep end. So the first one we're going to look at is instantaneous to induced dipole bonds or dipole-dipole bonds. So as I mentioned earlier, some of your exam boards call this van der Waals. Some of your exam boards call these London forces. It's the same thing. Oh, I forgot that my face is in the way of that corner, isn't it? Okay, hang on. I'm going to write that down. Can you see the words London forces and van der Waals now? Is my face still covering them? Are all linear shapes non-polar? So not quite. So if on either ends of the linear shape, you have the same atom. So like with our carbon dioxide, it was an oxygen on both sides. So then yes, that is the linear shape makes it non-polar. But if those atoms on either side had different electronegativities, then you would have a dipole. Face. What does face mean? Does that mean that you can see it? I'm going to assume that you can see that it says London forces. CN would be polar, wouldn't it? Yes, it would. Okay, so I'm going to move forwards. So an instantaneous to induced dipole bond, or London force, is the kind that we use to describe the intermolecular forces of sort of non-permanent dipoles. You can't see London. So if I'm talking about non-permanent dipoles, does anyone want to drop in the chat, like if it doesn't have a permanent dipole, how does that work? How does a non-permanent dipole work? How does it form? Are you late? Yes, you are, but that's okay because it's not a normal class. So you can just pop in when you feel like it, as long as you don't mind, missing things that would help you. Temporary dipole, electrons are constantly moving, it's induced by others around. Yeah, all of these are lovely answers. So are you late, Riaz? I don't know if you just turned up. Yes. So I'm going to use methane as my example, and I can see lots of you guys are putting some very useful things in the chat. So if we take methane, yes, carbon and hydrogen have like super similar electronegativities. So if you use the like actual values. I think one has like 2.2, one has 2.5. So a 0.3 difference in electronegativities in the Pauling scale is not significant. It's not a permanent dipole. But electrons never stay still. They literally cannot stop moving. So even though on average they are evenly distributed between a carbon and a hydrogen, they are always moving. So like at one point, the electron density might be over to this side of the bond. And at another point, it might be over to the hydrogen side of the bond. And at another point, it might be sort of completely evenly distributed between the two. And this is just the nature of electrons. You're right, Mitch, the clouds do influence each other. And we will get to that in the next sort of box. Angelo, yes, you can watch this later. Okay, so if we have electrons moving around all the time, lots of you have said things about the electron clouds influencing each other. What do we mean by that? What is, so Sofina, you also said induced dipole. Explain that a little bit more for me. Anybody? What are the forces involved here? The H could become more negative, and it forms a negative charge, which induces the neighboring atom. Yeah, so I'm going for positive dipole on one induces a negative dipole on the other. Yes, so Ghazal, and Ghazal, if I'm pronouncing your name totally wrong, please tell me, has got the word I was looking for, repulsion, to repel. So a dipole of one atom will repel or attract the electrons of another molecule next to it. So I'm going to keep with my methane example, and I'm going to sort of choose to assume that it has a sort of non-permanent dipole formed randomly in the moment, so that my hydrogen is for a split second delta positive and my carbon is for a split second delta, did I say positive? The carbon is delta positive, the hydrogen is delta negative. So any of our nearby molecules, let's say you have it oriented this way, they're going to experience repulsion of their electrons. So even if the electron density had originally been sort of even between our hydrogen and our carbon, when it sort of gets near that delta negative hydrogen in the other molecule, it repels the electrons. So you form another dipole, even though both of these molecules technically don't have a permanent dipole. You sort of randomly caused an actual dipole. And it could happen the other way around, right? Like if that first hydrogen had been delta positive, then the electron density in the other molecule would have been attracted towards it, still causing a temporary dipole to be formed. Everybody following me so far? Yes. Oops. Wicked. All right, so we have two things with non-permanent dipoles formed. One, because it happened instantaneously, hence the instantaneous part. That sort of also means randomly. And one that happened to be induced by an instantaneous dipole. So that's the induced part. So Angeline says, why does the delta negative repel the electron? So that's sort of our normal sort of, if something is negative, it repels other negative things. If something is positive, it attracts negative things. So that's sort of our sort of basic electrostatic attraction at work. So if you have a delta negative, that means that you've got a higher concentration of negative charge. So any negative charge around that is going to be repelled. Does that help? Would the molecules repelling from each other cause a decrease in boiling point? So boiling point is one of those things that is a property that depends on like millions of molecules at once rather than the action of an individual molecule. So the boiling point is going to depend on the intermolecular forces of all of the molecules in the mixture, rather than just sort of like one happening. Does that make sense? You thought electronegative is delta negative. Yes, so a delta negative or electronegativity means that you have a higher density of electrons or a high density of negative charge. And so any other nearby molecule, its electrons are going to be repelled by that. Does that make sense? So like the electrons here causing this hydrogen's delta negative sort of push away the electrons in the molecule below. Does that help? Are we going to go over exam questions? Yes. Is London forces the same as van der Waals? It's often used interchangeably, so I'm just using them both interchangeably here. They do have slightly different meanings. Van der Waals is actually a bit of an umbrella term for like a group of intermolecular forces, but for the sake of A-level chemistry, you can use them interchangeably. Then does that induce a delta positive on the other? Yes, so the delta negative on one atom will induce the delta positive on another atom. So the delta negative pushed the electrons in another molecule away. So the hydrogen that was near the delta negative then becomes delta positive. Does that make sense? Angelina, have I helped at all, or is it still, am I still not explaining it well enough? Is this topic important in an exam point of view? All topics are. Yes. Otherwise, I wouldn't be telling you about it. Am I doing a class on carbon-13 spectroscopy? Oh, I don't know. Maybe at some point, Agatha. If enough people, basically, if you guys are ever like desperate for a class, the best thing for you to do is just to like go on one of our social media platforms, so like Insta, and just keep messaging us and get loads of people to message us like, please do this class, and then we will eventually do it. Okay, so if anybody is still confused, please tell me. I would much rather just keep trying to help if you are willing. But yes, so you thought if something is more electronegative, it will attract electrons more. So that's right, within the molecule. So electronegative describes the ability rather than the actual charge. So it's like, what's a good analogy here? So electronegativity is, let's say, this is a tricky thing to describe. So I'm going to write in this box, but we'll ignore this. I'll delete it afterwards. So electronegativity is the ability to pull electrons. I'm not going to finish the sentence with the whole inner covalent bond thing. It's the ability, whereas partially negative charge is sort of after you've said that an atom can pull electrons towards itself, its partial negative charge is the result of that. So electronegativity is like the cause, and the partial negative charge is the effect. So it's actually now got the electrons. So the electrons are there. Or electrons have arrived, right? So the electrons are actually there. So that means that even though we describe that atom as being, as having sort of high electronegativity, once it has that charge, surrounding things are going to be repelled. Does that help at all? So the electronegativity causes it to be more negative, which pushes other things away. So it's like steps in a process. Is that helpful at all, or not so much? I sense that it's not helpful. I'm trying to think of a good analogy to explain the sort of distinction between. Yeah, it does. Okay, good. All right. And then I will think about better analogies for next time, just so that this goes faster, because it is a tricky distinction to make. I do see that. All right. So I'm going to go back to our induction of a dipole. So our dipole has been induced. So we now technically have this non-permanent delta negative on our hydrogen. So that hydrogen sort of for a bit has more electrons near it. And we have a delta positive on a hydrogen in a nearby molecule. What's going to happen if you put a negative charge next to a positive charge? But should we consider the full valence shell of the hydrogen so it has no ability to attract another electron? So if you're thinking, Jake, about hydrogen on its own, then hydrogen is not very electronegative, you are correct. But electron density, sort of think of it as an effect of the whole molecule rather than just the hydrogen. And thank you, Ghazal. Yeah, they're going to attract each other. The partial negative on your hydrogen is going to attract the partial positive on the other hydrogen, and you're going to get a weak electrostatic attraction. So this is a weak electrostatic attraction. And that is the formation of our instantaneous to induced dipole bond, or London force. So this is sort of like a stabilizing effect, but it doesn't last very long. So because, as we've said, electrons move around a lot, and these aren't permanent dipoles, they're just sort of randomly formed. If any other molecule with some kind of partial charge comes along and bashes into any of these, the charges are going to move around and the connections, the weak electrostatic attractions are going to break. So this is why things like methane are gas molecules rather than liquid or solid, just because those electrostatic forces, they're very sort of wibbly. They don't last that long. Everybody okay with that? Can I move forwards? This is so easy. I'm glad you're finding it easy, FRS Gaming. That is a good thing. So an electronegative atom bonds with a less electronegative atom, so causes a permanent dipole. Sometimes, Omar. We'll get onto that in the next slide. Not always. I mean, like, things with the same electronegativity are perfectly happy to bond together. Like your halogens, for example, chlorine, perfectly happy to bond with another chlorine. And that's not going to have any difference in electronegativity. All right, I'm going to move forwards because nobody's saying not to. Feel free to tell me to go back. Hydrogen isn't a molecule, so how is it an intermolecular force? Hydrogen's in the molecule. So we have, Zara, it's within the methane. These are methane molecules. If it's weak, is that why it's called a partial charge? It's called a partial charge because it's not a formal charge, i.e. it hasn't actually lost an electron or gained an electron, so that the ratio between the charge of its nucleus and the protons and its electrons surrounding it, for something to have a proper charge, it has to be unbalanced, the number of protons and electrons. So these don't have unbalanced numbers of protons and electrons. They just have the electrons sort of shifted in one direction. So it's like kind of like a charge, but not really a charge. So does that help? So electronegativity in a covalent bond is always changing due to the moving electrons. Yes, Camille. And this is more important in things that don't have a permanent charge, because it causes things like these instantaneous to induced dipole bonds. It matters less if there's a permanent partial charge or a permanent dipole, because then even though they're always moving around, they're sort of more likely to be found on the electronegative atom, even though they technically still are moving. What time is this webclass until? 1-ish. Okay, I'm going to move forwards. Please let me know if you have any more questions. Right, so we just looked at the situation that occurs when you have non-permanent dipoles. So i.e. the situation when your electronegativities of a carbon and a hydrogen are the same-ish or very close, and there's no sort of permanent partial charge anywhere, and it's all about electrons moving. Other molecules do have permanent dipoles. So they have a really, really electronegative thing bonded to quite an electropositive thing. So the partial charges sort of sit there permanently. And I just dropped my pen, 1 sec. Ooh. So can anyone think of an example of something with a permanent dipole? And please do not pick something with oxygen, fluorine, or nitrogen, because that's a bit different. And we're going to look at that on the next slide. Any molecules with permanent dipoles? Anybody? I can't tell if there's just like a lag or if nobody has any. Tell me humans. HBr, yep, hydrogen fluoride, lovely. Carbon and chlorine, hydrochloric acid, yep, hydrogen iodide. Magnesium iodide does not count because remember that when we're talking about electronegativity, it's just covalent molecules, whereas magnesium iodide, we've got a metal and a non-metal, so that's going to be ionic. You think there's a lag? Okay, there's just a lag. My internet is sad. Yep, cyanide, hydrogen cyanide also counts. I'm going to use chloromethane just so that we have a direct comparison. But all of those were really excellent examples. Yep, chloroethane also, yeah, good one, Newton. Libby, the sort of hydrogen sulfide, also a good example, bit less of a difference in electronegativity, but still a difference. All right, cool. So I'm going to use my chloromethane. What are my partial charges? Where do they go? And as there's a lag, I'm going to ask my next question also, so that by the time you've answered the first one, I will be able to see the second answer on the chat. So my first question was, what are my partial charges? My second question is going to be, if I want to form a weak electrostatic attraction with the other molecule, how does that molecule need to be arranged? So partial charges first. Yeah. And I finally got your messages through. So we have a delta positive on the carbon and a delta negative on my chlorine. That is correct. So if I have a nearby molecule and I want to draw myself a permanent dipole, which way round should I be drawing it? Does it need to have the carbon near the chlorine on the other molecule, or does it need to have a chlorine near the other chlorine? And I'm going to check on my internet real quick. Seems fine. Okay. Yeah, exactly. So anything positive needs to be next to something negative, or anything negative needs to be next to something positive. So I'm going to put it this way around. So I have my delta positive on my carbon and my delta negative on my chlorine. And then again, I get weak electrostatic attraction between those two things. So even though I've called both of these things weak electrostatic attraction, which one is a stronger intermolecular force? The permanent to permanent dipole bond or the instantaneous to induced dipole bond? Anybody? Which one's going to be stronger? Yeah, my permanent dipole bonds are stronger. And this is just a probability thing, right? Because it's a permanent dipole, you have a higher probability of these weak electrostatic attractions forming over the instantaneous to induced, which is a little bit more random. So at any given point in solution, if you have permanent to permanent dipole bonds, you're much more likely to have them exist at a higher quantity than your instantaneous to induced, which means that things with permanent to permanent dipole bonds are quite likely to be liquids rather than gases. So all of these link pretty well to the properties of things. Okay, I'm going to move forwards. Is everybody? Why does the carbon not have a positive charge? Why does the carbon not have? Okay, so the carbon has a positive charge rather than the hydrogen because it's the carbon that's directly bonded to the chlorine. So intermolecular electronegativity is sort of directly between two things that are bonding. So the carbon is bonded to the chlorine pulls the electrons in the carbon-chlorine bond towards itself. Does that make sense? Yes, no, maybe. Otherwise, are people good for me to move forwards? Will intermolecular forces induce significant changes in the molecular geometry of the molecule? So, not really. So if you're thinking about the shape of a molecule, the greatest factors involved are going to be the sort of intramolecular bonds. So intra meaning within the molecule. And because those are covalent bonds, those effects are like huge compared to sort of weak intermolecular forces by several orders of magnitude. So the shape of the molecule is definitely determined by the sort of intramolecular bonds. So your lone pairs and your covalent bonds, that's going to determine the molecular shape, whereas your intermolecular forces for these small covalent molecules is going to determine things like physical properties rather than sort of stuff within the molecule itself. You don't get it. Okay, so I'm going to try and train you guys to ask good questions, because when you say I don't get it, what happens is it means that I have to go on like a hunting expedition to sort of figure out where it is that you are not getting things. And at some point when you get to uni, your lecturers aren't going to do that. So I want you guys to learn to ask good questions. So if you can cycle back in your head and be like, okay, I got this bit, I understood this bit, but here in this moment, I got lost. And then ask me sort of, how does this bit connect to this bit? Or ask me a question about that spot where you got lost. And that's going to be way more useful for you in the long run than if I go on a hunting expedition for where you got confused. So Fatiha says, so if the carbon is delta positive, then are the hydrogens delta negative? No. So the hydrogens are still a pretty similar electronegativity compared to the carbons. So the hydrogens, they're probably around the same level of electronegativity compared to the carbons. So we wouldn't draw a partial charge because there's not really a difference between them. So I'm going to move forward. But Omar, if you want to sort of ask me a specific question about sort of where things got confusing, I will definitely go back. So I'm going to give you a bit of time to think about that and move forwards a bit to my hydrogen bonds. So we just looked at permanent dipole bonds, and I said, don't pick things with a certain elements because that's going to be a different kind of intermolecular force. So if you can think back to the last slide, can you tell me which atoms those are, which elements form hydrogen bonds instead of just normal permanent to permanent dipole bonds? How is this different from temporary dipoles? Okay, so permanent dipoles are always there, and they are because there's a difference between the ability, like the inherent ability of a certain element to pull electrons towards itself. So permanent dipoles form when things like chlorine which is very, very electronegative, meaning that like it has an inherent ability to pull electrons towards itself, bonds with something that is not very good at that. So that's when permanent dipole bonds form. It's about sort of like the abilities of the atoms, whereas instantaneous to induced or London forces, they are not because of the ability of any one element to pull electrons towards itself. They are because electrons move around randomly. So they sort of form like for a split second, they form dipoles, but they're not lasting. They don't exist all the time. Does that make sense? And those of you saying nitrogen, chlorine, and fluorine are correct. So they form between hydrogen and oxygen, nitrogen, and fluorine. And those of you saying enough or NOF as a way of remembering it, perfect. Do I come live every Sunday? No, we have one class each Sunday, but it cycles around in the subjects. Blah, 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 blah. So we have oxygen, nitrogen, and fluorine. And these are like your permanent dipoles because oxygen, nitrogen, and fluorine are very, very electronegative. They are so electronegative that when they form electrostatic attractions with hydrogen, it's such a strong intermolecular force that it's technically a different kind of intermolecular force. So hydrogen is like super, super teeny tiny. So when it forms sort of intermolecular forces with these very electronegative things, it's like a whole different story. It's a lot closer to something like a covalent bond than it is to something like a very, very, very weak instantaneous to induced bond. Chlorine is not one of them. Don't try not to make that mistake. It's just nitrogen, oxygen, and fluorine. So I'm going to use water as our example because that is sort of the most common one that you guys will come across. So I'm going to draw my water molecule. And then we're going to draw some intermolecular forces between water molecules. So can I first have partial charges? Because that's where we should definitely start. Partial charges, please. And there is a lag, so I'm just sort of waiting for it to appear. H is delta positive, oxygen is delta negative. Yeah, lovely jubbly. So delta positive for my hydrogens, delta negative for my oxygens, and these are permanent dipoles. So they sort of are quite constantly there because oxygen as an element has the greater tendency to pull electrons towards itself. So we have a delta negative oxygen and a delta positive hydrogen. If I want to show some intermolecular forces between this water molecule and another water molecule, for hydrogen bonding, there's some pretty important ways about the way I draw it. Does anybody know some of those things that I like absolutely have to do? Dotted lines, yeah. Anything else? It's got to be at 180-degree angle. Yes, and it has to be between the lone pair. Yeah, beautiful. Okay, so the reason that hydrogen bonds are so different and so much stronger is because they form directly with the lone pairs on oxygen. And that means it has to be 180 degrees. So this angle here must be 180-degree angle. So what other kinds of bonds that are actual covalent bonds do you guys know of that form between lone pairs and other things? Anybody remember any? Yeah, coordinate bonds. So this is why hydrogen bonds are so strong. They're sort of like edging into coordinate/dative bonding territory. So they're sort of, they edge towards covalent bond character more than you would expect something that's just an intermolecular force to be. So that's why the bond angle is so important, because it's a lot more like a covalent bond where it stays at a constant geometry rather than sort of being wibbly wobbly. So that's an important thing. You need to make sure that you draw your partial charges. You need to make sure that it is 180-degree angle, and you need to make sure that you have the dashed line from the lone pairs on your oxygen. And I'm going to sort of skip ahead because we're running out of time a bit. But I just want to reiterate that they are strong because hydrogen is super small, and oxygen, nitrogen, and fluorine are super electronegative. So, lovely people, are we good to do some exam questions? What do we think? Yes. Good. Good. All right, let's do it because we're running out of time. So I want to do these and then I will do some chatting. So the exam question says, a hydrogen peroxide molecule can be represented by the structure shown. And we've got hydrogen peroxide here. So you can see it's kind of like water, but it's got an extra oxygen. And the question says, hydrogen peroxide dissolves in water. State the strongest type of interaction that occurs between molecules of hydrogen peroxide and water. What's a dative bond? It's a coordinate bond. You might have heard it. You can either use the word coordinate or dative, and it's the kind of covalent bond that happens when both pairs of electrons from the bond comes from one atom rather than from one electron from each. So I'm going to let you guys answer my strongest interaction that occurs between hydrogen peroxide and water. And I am pretty sure there's a lag, but I'm still going to wait and think about snow while I wait for my internet to catch up with your typing. Oh, it is being very slow. Hydrogen bonding. Ah, there we go. It's finally popped in. Okay, beautiful. Yeah, it's hydrogen bonding. So I want to make it clear that technically all of the types of intermolecular bonds we've spoken to so far are happening between our hydrogen peroxide and water. So the instantaneous to induced, that still happens. The permanent to permanent dipole bonds also still happening. Hydrogen bonds also happening. It's just that because hydrogen bonds are so much stronger than the other two, it's really the only important effect in this situation. The other two are sort of very minute effects compared to hydrogen bonding. So even though all of them are happening, hydrogen bonding is like the main one. The next part of the question, and if you've already read it, start putting ideas in the chat so that the lag does not take too long. The second part of the question says, draw a diagram to show how one molecule of hydrogen peroxide interacts with one molecule of water. Include all lone pairs and partial charges in your diagram. So you guys are going to tell me what to draw. I am not going to draw anything without your permission. So please instruct me. You think you'll pretend the answer? Yeah. With this lag, it's kind of better if you just start typing your answers to things. If you can predict what question I'm going to ask, just start typing and send them, and then I'll probably get them by the time I actually ask the question. Just because the lag is not Not great. Please tell me what I should draw. Okay. Lovely. All right, so my lovely colleague has screenshotted what you said in the chat and sent it to me on a different platform, which seems to be working faster than this. So cool, perfect. Lovely. So I need to draw a water molecule. Sure, I will draw a water molecule in blue because water. And then I will draw, has anyone told me to draw hydrogen peroxide? Nope, just the lone pairs. Okay, so I'm going to do what you guys say. So I'm going to draw 2 lone pairs because my water has 2 lone pairs. Partial negative on my oxygen, partial positive on my hydrogen. Lovely. What else am I drawing? Is this it? How did I get here? Draw a cow. All right, while I wait for the lag, I will draw a cow. It's going to be a really bad cow. Okay, I tried. All right. Okay. I apologize for how bad this cow is, but I tried. Draw a dotted line between the H atom of hydrogen peroxide and the lone pairs of oxygen. Okay, lovely. So I take that to mean I should draw a hydrogen peroxide. So I'm going to draw a hydrogen peroxide, and I'm going to orient. How do I need to sort of orient my hydrogen peroxide? Anybody? Gonna assume I would like to assume that you've told me how, so that I don't wait for ages for you guys, for the lag to stop. But there's something important. Okay, somebody said 180 degrees. All right, so I'm going to orient my hydrogen peroxide so that my hydrogen is directly aligned to my lone pairs. And then also my oxygen is sort of at a nice 180 degree angle. And note that the question asked for all lone pairs and all partial charges. So I'm going to keep drawing partial charges on this, and I'm going to speed the process a bit because you guys told me the main bits, which is fine. And yes, my cow does seem to have high heels. I think it looks more like a pig cow. Why does oxygen have 2 lone pairs? So it's in group 6. So if it's in group 6, then it makes 2 bonds and has 2 lone pairs left over to form the valence shell. That's sort of a bit out of the, what's the word? I can't think of the word. Scope, that's the one. A bit out of the scope of this class because it's sort of stuff from a little bit earlier. But if you just remind yourself when you're thinking about how many electrons something has. So we've got 2 electrons in the inner shell, and then 1, 2, 3, 4, 5, 6 in oxygen's outer shell because it's in group 6. So it means it can make 1 bond here and 1 bond here, and then it's got 2 pairs of electrons either side. Will there be hybridization? What will be the hybridization of these bonds? So if you're thinking like sp3 kind of hybridization stuff, that's also way beyond the scope of A level. For water molecules, we only sort of look at hybridization in terms of hydrocarbons at sort of A level, but it works very much the same as your hydrocarbons. So you should still have sort of sp3 kinds of hybridization. So I'm gonna move forwards. I think we've got to leave it here, guys. because it's coming up to 1 o'clock. So I'm going to skip the next part of the class because these always take longer than I think they're going to when they're on YouTube, just because there's so many of you. So let us just sort of go on to the bit where I tell you about SnapRevise. So skipping past the properties, and feel free to do that part of the class in the booklet yourself. So all we did today is look at the actual forces. So we looked at instantaneous to induced, we looked at permanent dipole, we looked at hydrogen bonds, but we didn't sort of go on to chat about their physical properties, which you guys can do in your own time, now that you have all of the basics. So didn't take art GCSE. I did actually. I just didn't focus on my cow drawing. Yes. So I'm going to spend a few minutes talking about us, because part of the reason we do these YouTube classes is to tell you about SnapRevise. So we have what I think is a fabulous website. And I'm going to show you it very, very quickly because it's almost 1 o'clock. Blah, 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 blah. Show. And then I'll give you your discount code because I'm nice like that, of course. Blah, blah, blah. Let me share my screen with you. Okay, so I'm now wondering if my internet is going to allow me to load the website. So let's see if it actually loads, because obviously my internet is not handling the YouTube classes particularly well. So while the website tries to load, it did it, huzzah. Okay, so if you were to sign up for our classes, essentially there's like different levels of subscription you can have, but the sort of ultimate subscription is the one where you get live classes like these on our website. So for example, if you wanted to learn about the structure of the periodic table, the first thing you would do is do like a diagnostic quiz where it would tell you sort of what you do and don't know about that subject, like which ones you got right, which ones you got wrong. And then it would sort of point you towards some videos that would help you understand things that you sort of didn't get the questions right about. So it sort of tailors that bit to you. So you get a list. So I did not know about period 2 elements, but I did know about periodicity. And then you would get to watch a bunch of lovely videos, sort of explaining the bits that you do know. So notice like the green bits, the stuff I did know, has that sort of green. So I know that I don't really need to watch that part of the video, but I can watch the orange parts because that went a bit wrong. And then once I've done that and I've watched some exam question walkthroughs, I go to my exam pack and I try like this big bank of exam style questions that we built for you guys, because most people sort of complained that there's not enough past paper questions. So we made loads for you. So you would do that. And then if after you've watched the videos and you've done the exam packs, we also have web classes with people like me. Or my lovely colleague Alyssa, who is our other chemistry teacher, who has a class tonight at 6 p.m. about Le Chatelier's principle and equilibrium. And you can watch these classes and they're interactive like this one, or you can come to drop-in sessions and just ask us random questions about stuff that you're confused about. So we've built this whole platform to try and sort of be like almost like an online school. So that is sort of like the paid subscription. But if you can't afford to pay for this subscription, we will be here for you on YouTube. So this is sort of our compromise between wanting things to be free, but also wanting to be able to pay rent and stuff. So please do whatever you can afford, and I hope these things are useful for you. Kiana says, since they're incorporated A-level, oh, it's disappeared. Where'd it go? Since they incorporated A-level content into GCSE papers, is there anything high level like uni work on our work? Do you mean on SnapRevise, do we do anything like to help you prep for uni and stuff? The subscription it depends on sort of like which subscription you get. So the first, like the cheapest one is just the videos. And the next cheapest one is the exam packs and the videos. And then the more expensive one is the ones with the web classes. We are sort of changing things up a bit sort of soon so that you can just subscribe to the web classes, because I know some people were having trouble paying for all of the things and just wanted the web classes. So we're sort of also making a package for that. So if you have a look at the website, we do have like a list of the prices for things. But if you just want the web classes, sort of you can hold tight and just subscribe to those, and in a while when we set that up on the website. What else? Did anybody else have any other questions? Okay, no. So all I'm going to do then is share my screen with you so that you can see the discount code. Our actual A-level papers do have university content in our papers, like GCSE students have content in yours. So the syllabus did change so that they brought a lot of sort of first year university content into the A-level syllabus. So the sort of exam pack questions we have also do that, but they just do it at the same amount as the new syllabuses do. We didn't sort of add any extra bits, if that makes sense, Kiana. But yes, so make sure you set reminders for these classes. And then if you would like to subscribe to our lovely website, here is a £10 off discount code for your first month. And it is 1:03, so I'm going to go and eat some lunch and have a sundae and stuff. But it's been a pleasure. Do let me know in the chat if you've got any other very, very quick questions, and I might just get to them, but chances are the lag will be too much and I'll be gone before you ask them. So I'm going to go. Do you think it's possible for somebody to get 20% in tests up to this point in year 12 and end up with an A? Luke, it would really depend on why you were getting 20%. If you were getting 20% because, for example, you'd been ill, you've been unwell and it was just too hard to study, and you found good strategies to deal with your illness, or the illness has gone away, then it might be possible. It might take you another year. You might have to sort of spend another year studying just to make up for lost time. If it's because you've been procrastinating and you're finding it really difficult to get yourself to study until you solve that problem, I think it's unlikely. So it really depends on why. If it's because you just find chemistry really hard, and even though you've looked at lots of different resources and you've asked your teachers for as much help as you can possibly get, and you're studying for hours and hours and you're still getting 20%, it might just not be your subject. That's not a definite thing ever. I would never encourage someone to, quit if they love chemistry. But yeah, it really depends on why. Will the AS be cancelled this year? Do you mean the exams? All the exams are sort of cancelled nationally, but schools and colleges and sixth forms should be sort of doing their own assessments. But yes, I'm going to go. And the A-level. So yes, so if you guys have been keeping up with the news, the actual the national exams have been cancelled, but to give you a grade, if you're in year 13 or sitting just the AS, your teachers will be sending you some kinds of assessments. I'm going to go. I'm going to go have some lunch. But as I said, it's been a pleasure. Have a lovely day.